Hi, everyone. Welcome to Exponential Functions. We are starting this unit today. I hope that you all had a wonderful spring break. Throughout exponential functions, we are going to learn how to write an equation of an exponential function. We are going to learn how to graph an exponential function, and we're going to revisit evaluating exponential function equations this week. So let's get started. Always tying this content into a real world application, there's nothing more fitting than what's going on in the world around us right now, which is obviously the COVID-19 virus. We are hoping that by staying home and sheltering in place, we're flattening the curve. I'm sure you've heard that on the news or reading it online. And basically, what that means is each of these data points represents the number of cases that people have contracted this virus. And it starts out pretty slow. It's not increasing all that much. But then what happens is we've had a very, 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 very quick increase in the number of cases. And so when they talk about flattening the curve, what that means is they're trying to get this steep increase to not be quite as steep. And we'll talk about that more throughout the unit, but that's just a perfect example of a real world application of exponential functions. So I want to start with y'all by reviewing functions. We can look at a function through a verbal description or a word problem. We can look at a function represented as an algebraic equation. We can look at it in a table, and we can look at it in a graph. At the very beginning of the year, our first function focus was linear functions. And a linear function, as mentioned on the previous slide, can be represented in a verbal description, such as, you are driving to visit your best friend in Gulfport. Since you have a long drive ahead, you turn on your cruise control. The cruise control keeps your car traveling at a constant rate of 60 miles per hour. If you were to read that in class, we would say, okay, well, let's pick out your keywords. What words are telling you what's going on? Here, the MPH stands for miles per hour. Per is one of our keywords on our word wall that tell us multiplication's happening. What we know also is that constant tells us that things are staying the same rate, the same speed in this case. So that's how we know that this is in fact a linear function. We can also see this linear function represented as an algebraic equation. So we could say f of h equals 60 times h. Your distance traveled, or f of h, in miles depends on your time, h, in hours. If we look here, f of h tells us that we do in fact have a function. F of h is the same thing as y. It is your dependent variable. 60 in this equation comes from the verbal description, 60 miles per hour. And h is representing your hours that you're spending traveling. So 60 miles per hour. 60 in this case would be our slope. We can look at this function in a numeric table where h is your independent variable. Those are your hours traveled. So if I traveled for 3 hours, f of h, or my total distance traveled in miles, would be 180 miles. These are my ordered pairs. If I traveled for 5 hours, I would have driven 300 miles. If you notice, each of the dependent variables is increasing by 60. That constant rate of change, whether it be increasing or decreasing, tells us that this is in fact a linear function. If we were to look at this function graphically, linear does in fact mean that it is a straight line. So we have our independent variable, which is our x-axis, our dependent variable, which is our y-axis. So we have hours and distance traveled. And so you could take each of these ordered pairs over here and plot them, and they would all fall on the line, all representing the total distance traveled in this linear function. After we talked about linear functions, we talked about quadratic functions, and so that was our most recent one. If we looked at a verbal description, such as, you are observing the height of a ball as it's dropped from a 150-foot tall building. Because of the force of gravity, the more time that passes, the faster the ball travels. The ball does not travel at a constant speed like your car on cruise control. An algebraic equation, the height of the ball h in feet is a function of or depends on the time t in seconds. Okay, the quadratic function can be represented by the equation h of t equals negative 16t to the second plus 150. We learned in class that anytime you see that exponent 2, the power of 2, we know that's going to be a quadratic equation. If I look at a quadratic function in a numeric table, I cannot see a common rate of change. Whether it be increasing or decreasing, I cannot find that with the first differences. This one happens to be decreasing because the ball is falling. If I were to find the common difference of each of the first differences, I would in fact then be able to see that it is in fact a quadratic function. If I looked at this quadratic function graphically, I have the ball at the top of a 150-foot tall building. All right, that's seen here. That is our y-intercept, also our starting point. It's the number all by itself. And the ball is falling. Gravity is pulling it all the way down. If I look along the x-axis, it took just over 3 seconds for that ball to fall down to the ground. The slope is negative. The parabola is opening down because of that negative. And so we know that anything raised to the power of 2, okay, is going to open down. This is a parabola opening down. A parabola, remember, is that U-shaped. I hope this quick little review of linear and quadratic functions was helpful.